All right. Good morning, everybody. Welcome back. So today we will start chapter number 5. Chapter number 5 will talk about the properties of gases. It's a very short chapter and should be very simple. So let's start it today. And then I will stop around 11:25, and then we will have our traditional in-class assignment. Okay, let's share my screen with you. All right, start chapter number 5. Okay, so in this chapter, we will first cover gas laws. After that, I will talk a little bit about stoichiometry and how to quantify the amount of gases produced in chemical reactions. And then the last part of the chapter will cover a mixture of gases, the kinetic molecular theory of gases, and the real gas. All right, so let's start with some questions and some observations from day-to-day life. So the first picture I'm showing you here on your left side, if we fill two balloons, one with helium and one with CO2, we will observe that the balloon with helium will float, will tend to go up, while the balloon with CO2 will sink in the air. Okay. So we need to answer this question, and that's one of the goals for this chapter. And the second figure that I'm showing you on your right side here, especially if you live in Southern California in a very hot summer day, if you fill up your bike tires too much and you go for a ride, you have a really high risk of blowing up your tires. And uh, again, we need to explain why that. All right. So with those questions being set, we are ready to start talking about gases. Then let me switch to the other screen because it's going to be easier. Okay, so let's first talk about the characteristic of gases. So gases are compressible and immediately fill the space available to them. Molecules of gases are widely separated and in ceaseless chaotic motion. In other words, gases, they fill up the space of the flask, therefore they don't have their own volume, and the molecules are moving in a random motion, and the movement is chaotic. So no order on the movement. To characterize a gas, we need to know three different things of the gas. So as a person, to characterize a person, you need to know height, color of hair, color of eyes, and color of skin. So that helps to characterize, to ID a person. And with gases is the same thing. If we know pressure, volume, and temperature of a gas, that's enough to characterize a gas. So let's start here with the first variable, which is pressure. The symbol for pressure is a lowercase p, and the pressure results from the collisions of the gas molecules with the walls of the flask. So imagine that the gas molecules are small balls and they are moving all over the place. And when they hit the walls of the flask that contains the gas, that will create pressure. Pressure is equals to the ratio between force and area. And attention here, the unit of pressure in the international system is Pascal, okay? So that's the unit for pressure in the international system. And Pascal is equals to newtons over squared meters. Other common units for pressure. ATM is a very common unit. 1 ATM is equivalent to 1.01 times 10 to the 5 Pascal. And the other very common unit for pressure is called Torricelli, and the symbol is Tor. And the equivalence here is that 1 ATM corresponds to 760 torr. Volume. Gases do not have their own volume. Therefore, the volume of a gas is always equals to the volume of the flask. And the unit for volume in the international system is cubic meters. Another usual unit for volume is liters, and the correspondence between cubic meters and liters is that 1 cubic meter is equivalent to 1,000 liters, or 1 times 10 to the third. And finally, the last variable that we need to know to characterize a gas is the temperature. Always look the temperature of something that's proportional to the kinetic energy of the gas molecules, okay? So look at temperature as the something being proportional to the amount of vibration or the speed of the gases molecules. Higher than the temperature, higher the speed of the gas molecules moving around. And lower the temperature, lower the speed that the molecules move around. For the temperature, always be careful because the unit has to be always in Kelvin, okay? Always Kelvin. If the temperature is given in Celsius, you have to transform for Kelvin. And that's here is how you transform from Kelvin, from Celsius to Kelvin, okay? Temperature in Kelvin is equals to temperature in Celsius plus 273. And that's the conversion between the two units. We always use Kelvin because Kelvin does not accept negative temperatures. It's an absolute scale, and that's why it is used. And it's the unit from the international system as well. Okay, so now that we know that we need to have a knowledge of pressure, volume, and temperature to characterize a gas, we need to find an equation that correlates all those three uh, things, okay? And to start studying gas, we will first talk about an ideal model, and that's called ideal gas. So let's ask something here. Hey, Zara, are you here?
Yeah.
Okay, so if I ask you, what are the ideal characteristics for your ideal partner? What would you tell me? What your ideal partner has to have?
A job.
A job, that's very important. What else?
Um, I guess a good personality.
Good personality. What else?
Wow, this is a lot of pressure. I don't know. I guess likes to do do things, go on adventures, stuff like that.
Awesome. Job, nice personality, likes to go on adventures. What about height? Tall?
Height.
Yes.
I'm pretty short, so I actually don't care.
You don't care? Okay.
Nah.
What about hair color?
Um. Oh, I don't care.
So you're pretty easygoing.
Yeah.
Well, thank you very much. Well,
Okay.
guess what? Your ideal partner does not exist, unfortunately. Okay.
Oh.
So sorry to
Okay.
tell you that.
That's
So
okay.
ideal things is something that we create to make things easier, but they are far from the reality. And that's the same thing here with an ideal gas. Ideal gas is an exceptional situation that may happen if we force a little bit, but it's very useful to start studying something, but it's far from the reality. So at some point, you have to correct your expectations and just deal with the problems, okay? And that's what we are going to do when we study the real gas. So let's start with the ideal gas, which is pretty simple and covers part of the observations. What are the characteristics of the ideal gas? First, the intermolecular interactions are neglected, okay? So we are going to consider that each molecule does not see each other. Second characteristic is that the volume of the molecules are also neglected, okay? So the gas molecules, the volume of the molecules is so small when compared to the flask that we can neglect it. And there is one situation that the real gas has the same behavior as the ideal gas. And let me note here. So we can observe ideal gas behavior just write this here. So we can observe ideal gas behavior when we have low pressure and high temperature. Those are the situations when we will observe the ideal gas behavior, okay? So a combination of low pressure plus high temperature. The high temperature will ensure that the speed of the molecules is so high that they don't have time to interact between each other because they will cross each other so fast that the interactions are neglected. And low pressure means that the gas molecules are so diffuse compared with the volume of the flask that we can neglect the volume of each individual molecule. And then the equation that correlates pressure, volume, and temperature is called ideal gas equation, or also called Clapeyron equation. And it's the one that I'm showing you here. P times V equals to N times R times T. So let's see who is who in this equation. Starting first with P. P is going to be the pressure of the gas for the pressure of the gas. The unit in the international system is Pascal. And let's note here. So that's when we are in the international system. And we can have another unit, which is atmospheres or ATM, and that's a very usual unit to use. The second term of this equation is volume. The unit for volume in the international system is cubic meters. And the usual unit for volume is liters. Okay, so that's an usual unit. The second term, sorry, the third term in this equation is N. N stands for number of moles. And for number of moles, there is only one possible unit, which is mole. And that's also the International System unit. I'm going to move now to temperature. Temperature here is the last term of the equation. For the temperature, always pay attention because the unit has to be in Kelvin, and that's also the unit from the International System. And there is here a very special term in the equation, which is R. R is called universal gas constant. Okay? Universal gas constant. And that will be given to you. The universal gas constant is very, very important when we are using the ideal gas equation, because the units that you have in the universal gas constant will determine all the other units. And that's the clue that you have to follow to figure out which units you need to use. For the universal gas constant, it can show up as 8.3 joules per mole per Kelvin. Okay? When you see that 8.3 joules per mole per Kelvin, joules means that the pressure has to be in Pascal, and the volume has to be in cubic meters. Mole is going to be the units for number of moles, and Kelvin is going to be the unit for temperature, okay? But like that. Always pay attention to the units of the constant, and that will determine all the other units that you have to use for the other components of the ideal gas equation. Another value for the universal gas constant that is also very common is 0.082. And the units here are going to be ATM times liter per mole per Kelvin. Again, look at the units of the constant, and then you will figure out all the other units in the formula. ATM will be the units for pressure. Liters is going to be the units for volume. Mole, the units for number of moles. And Kelvin, the units for temperature. Okay, so the situations that you have to use the ideal gas equation is when you know three things from the gas and wants to figure out the fourth thing. Okay, for example, you know pressure, volume, number of moles, and you want to figure out the temperature, or any combination of three known variables and one unknown variable. And again, this equation is only valid when we have an ideal gas. All right. Now that we know what an ideal gas is, and we know what is the equation that correlates pressure, volume, and temperature, now let's start talking a little bit about transformations. A transformation always involves a change of one of the characteristics. Okay, if you cut your hair, that's a transformation because that's a change in one of your characteristics, for example. And for gases is the same idea. A gas transformation involves a change in the pressure and or volume and or temperature of a gas. Okay, we can have a change of all of the three, or just two of them, or just one of them. Okay? For simplifying our studies, we will only consider systems where the gas cannot escape, or also called closed systems. In a closed system, the number of moles of the gas before and after the transformation is always going to remain constant. One very simple example of a gas transformation is a very simple experiment. If you take a plastic bottle, put the cap in, and cool down the bottle, you can leave in the freezer or the fridge or put in an ice bath, you are going to see that the bottle will shrink. Okay, so the volume of the bottle will decrease. We are changing one of the characteristics of the gas, in this case the temperature, and that will reflect in a change of the other characteristics here. If we are cooling down, the speed of the molecules is decreased. That means the pressure is going to change, and that will affect the volume in this case. Okay, I think that's a good point for us to stop for today. Next week, we will talk more specifically about three different types of transformations uh, in gases. And let's take a 3-minute break, and let's come back at 11:30 to do the in-class assignment. Okay, so I will see you at 11:30.